cyclostationarity. Cyclostationarity is an extremely relevant feature of many signals and time series, and a recent survey paper written by a friend of mine, Professor Antonio Napolitano, has shown about 5,000 papers in the recent decade dedicated to cyclostationary time series in signal processing, in finance, in climatology. So there is a huge room for applications. And what is the plan of my talk? I would like to start with just a very brief description, and then I'm going to give you a sort of a mathematical point of view on what cyclostationarity is and how the APC is the acronym for almost periodically correlated, which is a very convenient mathematical framework to work with a cyclostationary time series. And once this mathematical framework is established, I'm going to move on to more statistically motivated questions for non-stationary time series, such as estimation. Well, you know, the rationale for moving to statistical analysis is pretty simple. Once we have a good view, a good mathematical foundation on what non-stationarity in cyclical way or almost cyclical way is, then we would like to estimate relevant parameters of a signal to do many things like, well, hierarchy of signals, like identification of special features of signals, like short-term forecasts. So essentially, this part of my talk will be dedicated to estimating second-order characteristics of non-stationary time series. And well, as usual, in statistical language, when we do estimation, we would like to have some idea on how much we err. As they say, the truth is in the errors. So the errors of estimations are very important. That's why always when we do statistical inference, we are building a concept which is called confidence interval, which is a measure of error. And such confidence interval in classical statistics is based, well, on some normality assumption. Unfortunately, for more complicated data structures, like a time series, building confidence intervals is not easy. So in recent 30 years, there is a very popular method of resampling called Bootstrap resampling that is leading to efficient, computationally efficient, and also theoretically appropriate methods of establishing such confidence intervals. And those acronyms, I hope, do you see when I'm moving my pointer across the screen? Can you see that? Oh, perfect. So, you know, the MBB is one of the many possible bootstrap procedures. MBB stands for moving block bootstraps for almost periodically correlated structures, and then generalized seasonal block bootstrap also for periodically correlated. Also, the third procedure is called subsampling. The results on those three methods are pretty recent. They were established well within, let's say, a group of my colleagues, working colleagues. Part of those results were established by my former PhD, now a professor of statistics. So there was quite a bit of work to have these results established. They are pretty heavy in terms of probabilistic theory. In order to show you theorems, I'm going to invoke such concepts like mixing, which is asymptotic independence, which is also not a very popular concept in statistics, but it's increasingly important for dependent data structures. And then when I'm going to move to the fifth point of my presentation, I'm going to show you some applications. The applied part of my research recently is mostly related to vibromechanics. That is, I'm going to show you the real signals coming from rotating machines, and using the procedures, we will be able to actually do identification of machines working properly and improperly. Why this is important? How cyclostationary signals are becoming important? Well, part of my research was done in a research center related to French railways in France. And these days, the high-speed trains have the, let's say, rotating elements. Imagine that the high-speed train these days in France is moving with the a whopping speed of 350 kilometers per hour. And the Wilby rings or anything rotating on this terrain can be observed online by direct sensors. So being able to process this information and have early warning on any possible improper functioning of, let's say, rotating elements is absolutely fundamental. Then at the last part of my talk, I understand I'm supposed to end in about 40 minutes, so maybe last 10 minutes will be dedicated actually to using Hilbert space to do dimensionality reduction of the signals and how Hilbert space analysis, so-called functional data analysis, which is essentially a Hilbert space analysis for big volume data, can actually improve our thinking and actually can reduce many millions of observations we collect on signals. Okay, so that's essentially the plan of the talk. Let me go ahead and start with the popular examples. Cyclostationary time series in the past were related, for example, to a time series of river flows. You have certain seasonality, but let us not confuse seasonality with cyclostationarity, because cyclostationarity is a property of the second order characteristics of time series. Seasonality is usually the flow of the mean, while cyclostationarity is also some periodic behavioral variance. So the upper picture represents the original data, and simply, your eye can tell you that it looks pretty seasonal. But then after deseasonalizing, after deducting, as we say in time series analysis, after filtering out the first order component, you can also see cyclical bumps in the second order characteristics. Another very good example is the engine signal. So any one of you can observe a cyclostationary signal. It's just enough that the conference will be over. You enter your car, you start the car and let the engine idle for a couple of minutes. And then if the engine works properly, it should have the rotation of 800 revolutions per minute, and the sound should be smooth. If there are any coughs, any bumps in the sound, well, this is the first signal maybe of your engine not working properly. And that's another very, very popular way of trying to identify, improper work of some vibrating mechanisms. Zooming down to the let's say, rotating machine, we have a very, very precise example of a wheel bearing signal. On the left-hand side, you have a properly functioning acceleration signal from the wheel bearing, which is already centered. The center of this picture is at 0. The 0 level provides a center, so it's a centralized signal. And this is the signal, which is also centered, but that corresponds to a wheel bearing that has some improper functioning. In this case, is so-called inner race default, the default of the inner race. So you can see at least visually that the second signal has a little bit of a higher variability. Now, how to classify, how to come up with the appropriate model to the system that is non-stationary is a challenge that we are going to overcome right now. Now let us move to a maybe more familiar to every participant of this conference, language of mathematics from the language of engineering. And when I'm saying a signal and time series, I really mean a stochastic process with the discrete time, but the discreteness of time is not necessary. It's just introduced for the sake of clarity of the presentation. It's just more convenient at this point to tell you that let time be discrete. We'll be calling such time series almost periodically correlated, APC for short, when the mean, the expected value of xt, and the autocovariance functions are almost periodic. Well, there are many senses of almost periodicity for real valued functions, and we are going to start with the most simple, that is the Bezzikowicz almost periodicity, which means every almost periodic function on the line can be approximated in the subnorm by the trigonometric series. That's the most convenient startup, but of course, you can have a more general concept of almost periodicity. And well, look carefully here where we have a covariance function. It is a non-stationary system because this covariance function depends on two arguments. A stationary case means it is irrelevant where you calculate your covariance as long as the time lag is equal to tau. The non-stationarity means, hey, also you need to take into account the starting point of your calculation. And actually in T, for the APC model, this function is considered almost periodic. That's why the name almost periodically correlated signals. And let me just remind you a couple of basic tricks related to statistical techniques for almost periodic correlation. There is, as professor having the presentation just before mine was very correctly making a point, there is a huge Hilbert theory related with stationary processes. And also there is a monograph written about 10 years ago by a friend of mine, Harry Hurd, and his colleague, Miami, on applying actually Hilbert space orthogonal projections to periodically correlated processes. You are absolutely right, Professor. There is this usefulness of the operators that actually are providing us a very concise and a brief description of the model. And I'm going to show you later on in my talk that this is also very relevant to the data analysis. But now just basic tricks. So as I was trying to make a point, we take the Bezikovich concept of almost periodicity, which means that the autocovariance function can be approximated by a Fourier series. So we have the coefficients, A, lambda, tau. So the lambdas are the frequencies. So when I'm going to use the concept of frequency, what I mean is the frequency corresponding to the Fourier coefficients of the autocovariance representation. For example, when we have just a stationary part, the only non-zero coefficient corresponds to the frequency 0. So the identification of non-stationary behavior in time series may be built up by approximating the coefficients and then seeing which coefficient is essentially non-zero for a non-zero lambda. For that, we need a good estimator of the coefficient, and such estimator in a discrete time is here. It's nothing really much more complicated than the usual smoothed periodogram estimator for a stationary case, but we need to have a little bit of a closer look on how we understand cyclostationary from the cyclostationarity from the point of view of those frequencies. So when we work with non-stationary systems, there is a need for two frequencies, the F1 and the F2. Wide-stand stationarity means that the only relevant frequencies are on the line, which is y equal to x on the main diagonal of the system. Cyclostationarity means we have the set of lines that are equidistant, and this distance is actually 2 pi over t, where t is the period. Because strictly periodic function is, of course, a very particular example of an almost periodic function. So cyclostationary signals that are extremely popular in engineering are simply a small, let's say, subspace of the almost periodically correlated signals. For almost periodically correlated signals, you have lines that are parallel but are not exactly equidistant. Why I'm showing you this picture? Because using the estimator just previously shown, using this estimator, you are able to identify lambdas that give rise to the non-zero coefficient. And then once those lambdas are characterized, lambdas are coefficients of shift for those lines. So here is the line corresponding to lambda equal to 0. There's no shift. Here, there is only one period. So lambda is the multiple integer of the 2 pi over t, where t is the period. But here, you can have many lambdas, which is creating a much more rich structure, better for the data description, but also more difficult from a statistical and application point of view, and also more interesting from mathematical point of view. So let me first present a result. You know, what kind of language we are using in statistical inference for cyclostationary signals, and what are the usual conditions that are sufficient to establish quote-unquote good properties of our estimate. Well, let us first look at the boundedness of the moments. So we do assume in this theorem, it can be generalized, but let's just start from something very basic. So we do assume that we have moments bounded. To some of you who work with, for example, heavy tails, this assumption may seem a little bit too restrictive, but that's the starting point. Secondly, we assume there is a mixing assumption. Now, what is the mixing assumption? Just to give you a very, very short idea, intuition on mixing. Many statistical results, like a classical central limit theorem, is established for the independent data structures. For time series and signals, independence is very far from the reality. We obviously have autocovariance, okay? Now, how far this autocovariance is reaching? You know, the alpha mixing means that we have a certain function controlling the dependence that goes appropriately quickly to zero. So think about the alpha xt function that is integrable even with the power delta over 4 plus delta. Well, which means this function essentially goes to zero with a certain speed. So that's our way of controlling the dependence. Now, when this control of dependence, look carefully that the control of the dependence, the alpha with the power delta over 4 plus delta, is related to the, let's say, heavy tails or the boundedness of moments. When we have this condition guaranteed for the signals, then we have a second condition, the condition of identifiability. If you think about those parallel lines, let us maybe come back quickly. I hope it's all right when I'm shifting quickly between the screens. Does it create any problem? Is there any, let's say, visual problem when I'm quickly moving from one screen to another?
No, it's not creating any lag.
Oh, great, great. So if there is any problem, let me know. So what I mean by separability of lambdas. Of course, when there is nothing but one lambda, there is no need for separability, it's just one lambda. If you have a cyclostationary case, then lambdas, being the multiple integers of the 2 pi over t, of course are separated because they are separated by a smallest distance. But in the almost periodically correlated case, it's not necessarily true. So we need this condition of separability of the lambdas, and the set of all frequencies is usually assumed to be a capital lambda. With these two conditions, we have a classical central limit theorem for our estimator. Why central limit theorem is so crucial for statistical applications? Because this theorem is enabling us to control the error of the estimator. The a hat minus a is essentially how much we err. So we know that from this theorem, we know that the order of the error is proportional to the inverse of the size of the observation. The capital T is the collect time, the size of the observation. And there is also a scale parameter. Well, this is a bivariate normal distribution. And the scale parameter can be calculated from what is known as asymptotic variance of the normal distribution. Well, it is a theoretical result. But for practical purposes, you will need to know exactly what is the scaling factor. For an engineer, it is not enough that I say, well, my error is proportional to the inverse of the square root of the collect time. This is not enough. I have to give an estimate of a constant that stands in front of this 1 over square root of t. What is it? Then, mathematical theory doesn't go very far. We have mathematical formulae, but they are not giving us a workable solution. And that's exactly this point is raising the need for the bootstrap. But maybe, to maybe do a little bit of interlude between theoretical result, let me show you some practical applications of the estimator I just developed and show you the asymptotic properties. So if this is the typical cyclostationary signal, and if this corresponds to the ball bearing working properly, so that's the, let's say, signal, we create an autocovariant structure Can you see the coloring? Is the red color and blue showing also on your screens? I'm just checking whether what I see on my screen is.
It works properly. Though this plot is a bit grainy, but I think it's just how plot is drawn in original. Looking at
well, you know, the pixel size can be better. I agree, but you know, this is not the graphical arts conference. I understand. I'm just
the
showing
color
you
is showing properly.
Right. So, you know, the red color corresponds to the higher values, and let's say the blue color corresponds to lower values. And the what is plotted here is the absolute value of the estimator. Because the estimator is a complex value. So, you know, to have the plot done in a more easy way, you know, we have the absolute value. And then we have a cut of this at the point tau equal to 0. You know, from such plots, you can try to identify the lambdas that give rise to significant values of your coefficient. Now, when we are moving to the burdering rolling element that is damaged, okay, this picture looks significantly different, and there is more variability. So if you have a good statistical test that is able to identify a significant contribution to the energy of the signal by a given frequency, well, you know, this is a first visual impression what estimator and confidence intervals can give you in terms of characterization of a system, whether it works properly or improperly. Okay. Now, coming back to the theory. Since, as we already know, the asymptotic distribution of the estimator has this inconvenient part that is very difficult to estimate, the asymptotic variance-covariance matrix of a bivariate normal distribution, we are going to use here the Bootstrap procedure, a resampling procedure that is known to provide at least as good as asymptotic results, confidence intervals, plus they work in more complicated case, okay? So let us first start with something very, very simple, okay? So I'm just trying to explain you right now within a couple of minutes how the Bootstrap works. So let us assume we have a sample from time series, which means this sample does not represent independent variables. Let us maybe for the moment forget that we have a non-stationarity, not to complicate the picture at the very beginning, but just to give you the idea how the Bootstrap works. So what is Bootstrap? Essentially, Bootstrap is taking the blocks of the data, putting them into some sampling system, and then reconstructing the data from the blocks. So it is like reproducing the data with some specific idea. The specific idea here in this technique is called moving block bootstrap, is essentially this. The starting point is J, and then the end point is just B observations afterwards. So we have the length of the data equal B, okay? We actually slide with this block along the sample, okay? And then we are having discrete values, discrete valued random variables, I1, I2, IK, with this type of distribution. That is, they actually hit with the same probability across all points between 1 minus 1 through n minus b plus 1, okay? That means we sample the blocks from the collection of all blocks. You can produce sliding this block along a original sample, and then you concatenate those blocks to produce, let's say, a new sample. It's not really a new sample because you are not going to have new observations. It is sampling with replacement from the set of blocks, okay? Because you can sample all the time the same block, the first one or the last one, but more likely it will be that there will be some variability in the blocks, okay? So for this new sample, we are recalculating our estimator. Maybe before I move to the next slide, let me do a little bit of more explanation. When you have this new sample, you recalculate your estimator, so you have a new point. And then you continue this procedure. That is, you slide again your block along the sample, you choose randomly with replacement from the set of blocks, and you concatenate to create a next new sample. You recalculate your estimate, and on and on and on, for example, 1,000 times. Okay. The mathematical question and mathematical statistical questions behind this idea is the following. Are we doing something consistent? That is, are we going to obtain asymptotically the same quantiles, the same time of distribution as the distribution provided by the general theorem? And in many cases, the answer is yes, but not in all cases. You have to be very careful because, for example, the heavy-tailedness of the data may come in the way of consistency of Bootstrap. Okay, that's why we are moving very carefully here. What I'm presenting right now is the theorem established by my colleagues with some of my participation, but also with participation of my PhD student, now Professor Anna Dudek from Akademia Górnicza in Krakow. This is this theorem. So starting point is the APC alpha mixing time series. Now, even with a slightly more restrictive moment condition, we assume that top class delta moments are bounded, and we have a faster decline to zero of the alpha function. That's why we call mixing alpha mixing condition, the alpha function that controls the dependence of the data. If this is true, then the MBB procedure is consistent. What means consistency in the Bootstrap world is the following. This procedure of Bootstrap will provide me some confidence interval. If I can produce 1,000 replicates of my estimator, I can build a histogram and I can take 2.5% quantile and 97.5% quantile. So I can get a confidence interval. But the question is whether this confidence interval is correct, whether my evaluation of the error of estimator coincides with what theory is saying about asymptotic normality. And the answer is yes, in this case. So we are actually using this for our purposes. But from the point of view of calculation, especially from the point of view of when we know what the period is, so let's make an assumption that we work with periodically correlated time series. Then we have a procedure which works slightly differently. It is a variation on the previous method, which is the generalized seasonal moving block bootstrap or generalized cell-zedic block bootstrap for periodically correlated time series, where we assume that the time series is periodic. So it's a very particular case of almost periodicity, that you have exact replication of autocovariance. We assume that small d is the length of the period. You may not necessarily know what it is. It's another pool of problems to know what periodicity. For example, many stock data time series corresponding to the stock returns show some periodicity, but it is always a challenging question to discover what is the period. Okay, and then the second parameter is the length of the block. And we, to simplify description of the procedure, we assume that the n, the length of the data, is proportional to the length of the block, and the index of proportionality is L. It's not really necessary, but just to have simplicity of representation. And we also assume that there is a proportionality between the length of the period and the length of the data. Okay, how the generalized seasonal block bootstrap works. Okay, first we choose the length of block B. Usually the length of the block should be proportional to the sample size. The question is, well, a little bit more precise estimation of the length of the block. Usually it is of the order of n to the power of the cubic root of n to the power 1/3. Okay, and when we have this block B, we create a bootstrapped sample, sampling from the not original time series, but for the time series which is sampled, okay? Sampled from the special set of replicates of the period. So we have some cycle on the sample size, and then we sample from the cycle. That's why the generalized seasonal block Bootstrap is the name, okay? And we are getting by this token a bootstrapped sample. And once you have the bootstrapped sample, the story repeats as before. That is, you calculate your estimator on the bootstrap sample, and you try to establish the consistency. And this is my theorem with Anna Dudek and Dimitris Politis, that is Paparaditis from 7 years ago, where we know that when the structure is periodically correlated, when we have slightly less restrictive moment condition than before, so we are allowing moments of the order 4. You always think, by the way, you always think of delta as something very small. So delta will not be 1,000. Well, theoretically it can be, but it will not be very convenient for us. And then the mixing condition, again, as before, related to the order of the moment. Then the GSBB procedure is also consistent. That this is reproducing the confidence intervals that you can get using the normal distribution. And what is the advantage of GSBB or MBB is that you can actually calculate those confidence intervals. How you do it? You replicate, let's say, 1,000 times your procedure, then you order your data and you can get quantiles. That's how you build up your confidence intervals, okay? The difficulty of this previous two theorems, that is the MBB and the GSBB, is introducing a second layer of randomness. The first layer of randomness is obviously generated by the data, but the second layer of randomness is introduced by this procedure of sampling with replacement from the data. And from, let's say, probability point of view, it generates a new probability space, a discrete probability space, in which you have to work, you need to establish your distributions in order to show the consistency. One of the way out of this problem is to work with another procedure, which is subsampling, where you don't do any random sampling with replacement. You simply slide a block of a log B. So you create a block BI that starts in the xi and ends in xi plus b minus 1. You simply slide it. For each block, you calculate your estimator, like this one. This is the version of our estimator calculated for the block. And then if your data is long enough, then you will have enough, let's say, parts, blocks of the length B. Those blocks are overlapping. You may have non-overlapping, but the easiest is to create the overlapping blocks, because then you have more quote-unquote replicates, okay? Then from those replicates, you can calculate your confidence intervals, and such procedure is also proven to be consistent. However, well, you know, we work with practical applications. The subsampling is more efficient for very complicated data structures, but if you know more or less that your data are strictly periodic, it is more precise and it is quicker to have your confidence interval using the previous two. So subsampling, improving theorems is easy, but in numerical applications is, well, not so excellent as the two other guys before. Okay, let me now show you the application to the signal. Okay, so you are now seeing the three pictures. The picture, well, let me put my glasses on. The picture on the left-hand side, what we are plotting here is the real part of the estimator of the autocovariance function. And what those segments represent, those vertical lines, are the confidence intervals obtained by the bootstrapping, okay? As long as the zero belongs to these confidence intervals, there is no relevant frequency, because then, as any statistician would know, if the zero belongs to the confidence interval, you will not reject the null hypothesis of the coefficient being equal to 0. The real frequency, which is anywhere here between 6 and 6.6 kilohertz, the lambdas are in kilohertz, is here, okay? You see there is, in this interval, in this little vertical red segment, of course, 0 is not a member. So that's the first discovery that, hello, we have the significant lambda. Another discovery, if you look carefully at this interval, the little point in this interval is the point value of the estimator. And those endpoints are the endpoints of the confidence interval. It is clear to see that for the finite sample, the sampling distribution of the estimator is not normal. Because if the word would be normal, then the little circle will be exactly in the middle of the interval. It is definitely not. So Bootstrap is also, the Bootstrap procedures are working very well in the case when you are not yet in asymptotic regime, that is, when you are not really very close to a normal distribution, okay? And, you know, the residual signal is for us like diagnostics, whether our model was working properly, okay? Now I'm moving to the last part of my talk. I understand I have probably about 12 minutes left until the end of my talk. So now I'll be showing the usefulness of the Hilbert space. First, before we start using technical language, why thinking about Hilbert space for signal analysis? Not only to characterize the covariance, but just think about the data represented by curves. When, for example, coming back to this example of a high-speed train, traveling, for example, from Paris to Lyon, you travel with the speed 350 kilometers per hour, and the sensors are attached to the moving parts. What is the frequency of observation? Well, on average, you will have 3 kilohertz or 6 kilohertz, which means 6,000 data per second. So in a couple of minutes, you will have millions of data. So traditional time series for this type of signal analysis is completely useless. That is, I mean, to think about autoregression for data that are just 1,000th of 1 second apart, doesn't provide any useful model. It is a recent trend. In a recent decade, there was really a growth of new approach to big data analysis. This is the case of big data, several million of data points generated just in a few minutes of observation of some vibrating signal, okay? How to use Hilbert space to help us, first of all, give a good description of big data, and then the fundamental point, as raised also in the previous talk, maybe from more mathematical point, is the reduction of representation. We will call it principal component analysis in statistics. It will be in the functional approach, in the approach of Hilbert space. So now down to the Hilbert space approach to time series. If we have a signal XS, S now can be continuous, that's okay, it can be discrete as well, no problem. And we are having the signal represented by the sequence of random functions. So from the probabilistic point of view, we think of those random functions as parts of stochastic processes, or let's say random elements with the value of the Hilbert space. So Z1, Z2, Zn are the random elements, not random variables, because in probability, when you say random variable, automatically by default, you think about real values. Then comes random vector, which means you are in the RK. When you say random element, you mean the values are in the infinitely dimensional space. In this case, we consider the Hilbert space as a very convenient infinitely dimensional space. So our data are curves. Now, what curves are appropriate for cyclostationary signals? Well, I will be indexing those curves by the period and by the, let's say, a number nu, which is always between 1 and the length of the period. So I'm chopping the big signal into periodic parts. And then instead of writing n, I will write small n times t, the multiple, how many periods I have in the data, and then what is left beyond the multiple integer of the period. Okay. And how we really work with the Hilbert space statistical theory. Instead of working with the autocovariance function, you need to work with the autocovariance and variance operator, okay? Without loss of generality, for the sake of this presentation, I will identify the Hilbert space with the space of integrable functions on 0, 1. Doesn't create any inconvenience to have any other representation. Well, I will need a basis function in which I'm going to express my operators and then my data as well. So the operators will be a linear operators from Hilbert to Hilbert, okay? And I also need to have a, a norm on the operator space. But what is my model? What I'm doing right now in front of your eyes is building up a very simple equivalent of a fundamental autoregressive model for time series. But now my data are not points, my data are curves. So what I'm doing here in equation number 1, I'm saying that my observation, the curve that comes n times period plus nu, think about period equal for it. Let's say the data are monthly fluctuations of your stock, and you observe stock transaction by transaction, which means maybe a couple of transactions per second. So easily you will have thousands of data per month. Let's say in month we have 26 or 24 transaction days, depending on the month. So this will be the length of the month, this will be the number of the month, and this will be a day. So your daily curves of transactions, or you chop your vibration signals into periods, and then you have the your current place of the signal. So this model claims that my current observation can be autoregressed, and the big phi nu is the operator, okay, that actually transforms the curve before into the current curve, okay? But of course, as in statistical thinking, we know that this model cannot be accurate. It's not 100% accurate. So we have the error. The error is also a curve, a random curve in the Hilbert space. The theory of Gaussian random variables or random elements with values in Hilbert space is very well developed. So, we have tools to work with epsilon, and also we have tools to work with the operators. Well, when I'm going to show this model to an engineer, the engineer will probably be very kindly nodding his or her head, but the question would be then how to estimate an operator. On a computer, we don't have infinite dimensions. We have finite dimensions. That's why the reduction of dimensionality plays an absolutely fundamental role in this business, in the business of fitting the Hilbert space to real data. How you do that? Well, let me show you the first steps. Well, when you are estimating on the basis of the data your operator, so anytime I'm putting a hat on the top of a capital of a Greek letter, that means this is a quantity that can be reproduced from the data, okay? This operator is equal to, well, the autocovariance order 1 operator times the inverse of the variance operator. With the inverses of the operators, as most of you probably know, in Hilbert's place, you have to be very careful. The fundamental role here is played by the eigenvalues. And this formula can be represented as the formula of eigenvalues. So if you look carefully here at the small p, what I'm doing, I'm chopping at certain point my dimensionality. That is, I'm trying to look for the optimal p that on one hand is small, and on the other hand is sufficient to describe the variability, the energy of the whole signal. So the name of the game in real statistics is to get a reasonable p, okay? If my data are curves, then p is infinite, but you cannot work in infinite. You have to have a finite number in order to calculate your estimator. How you are going to do that? We have a recent paper of my PhD student dedicated to that. I'm watching right now my clock. It looks like I have only 5 minutes left. So maybe I will skip some theoretical results, and I'm going to move to more, let's say, practical stuff. That is, the question is, usually working with practical signals for the cyclostationary signals coming with vibrations, the p equal anywhere between 10 to 20 was enough to reproduce 95% of energy. Why? Because we know very well from the theory of operators what is the relationship between the variance of the whole signal and the sum of the eigenvalues. The eigenvalues are non-negative because this is a covariance symmetric operator. The model I have introduced is called the periodic functional autoregressive model of the order 1. This is simply a generalization of autoregressive model order 1, which is absolutely a butter and bread approach in any time series class. The F stands functional, so now my data are functions, and the P stands for periodic, because I do work with data that have some cyclic approach, that they have some cyclic behavior, okay? I'm introducing, like in the case before, I'm introducing a bootstrap technique, okay? I'm introducing a bootstrap resample, and I can actually get replicates of the eigenvalues. So if I know what my P is, okay, I can reproduce the eigenvalues, I can create the confidence intervals, and I know, this is a recent theorem, that this moving bootstrap for this model is consistent. That is, we are getting the same distribution as from theoretical result. To finish my talk, let me give you a practical application. Okay, so let's say we are collecting a signal with the frequency 2.5 kilohertz. After 10 seconds, this means we have 25,000 data points. And what I'm doing, I'm chopping this data into segments. So you see segments. Well, of course, this chopping is really guessing what the period is. So there is a need for good estimator of your period. I'm assuming I do have. So look, in the columns, the data are arranged, let's say, in the row-wise order. So if I were to recreate the long signal, I will put segment 1, and then segment 2, and then segment 3. But smart chopping shows that, for example, in the first column, I have a little bit of replication, that it is not very far from reality to assume that this curve may come from the same random mechanism as this curve. Now you see that my data, one data point is the curve, okay? This is my one data point. This is the data point 5 moments afterwards. This is my data points, another 5. So 5 is the period, okay? And so we have columns here. I'm using my periodic functional autoregressive model to this data. I'm estimating the eigenvalues using the 1, 2, 3, 4, 5, 6. So a reduction to dimensionality equal to 6 is giving me 84% of description of the whole variance. The CPV is the coefficient of proportion of the variance. 84% reconstruction of the variance is quite a bit. So instead of having several thousands of data points, what I do have, I have 6 eigenvalues and I have 6 eigencurves. This is a perfect case of dimensionality reduction, and then doing diagnostics of the signal. This is another typical diagnostic pictures for the functional data analysis. On the main diagonal, this is a matrix of pictures, essentially. On the main diagonal, it's a picture of those eigenfunctions, and beyond diagonal are so-called scores. Why this is diagnostics? Because the scores should be almost uncorrelated. In very small print, I hope you can see it, you can see the correlations between scores. They are in the order of 10 to negative 5, 10 to negative 6, so they seem to be pretty small. Now, I would like to put everything together. That is, I'm trying to recreate the original signal, the 25,000 or several thousands of data, which are shown in black, by my model, which is red, okay? The reconstruction maybe is not perfect, but I'm clearly seeing where the bits are, where the important points of the preparation signals are. I think I'll maybe stop with this because my time, I think, is over. That's another, let's say, picture showing the diagonal. On main diagonal, you have the eigenfunctions, and beyond diagonal, you have the correlations of scores. This is a diagnostic picture corresponding to this model, and that's another reconstruction of the signal. And at the end of my talk, I'm giving some references, and I would like to thank you very much for your attention. Of course, I'm more than open to have any questions. Thank you.
Thank you very much. Do you have any questions?
I will probably stop sharing my screen unless you want me to keep.
So, may I have some comments anyway? You know, Bootstrap was discussed many times because Bootstrap cannot improve sufficiency of statistics. Bootstrap leads to a number of interesting mathematical theorems, mathematical investigation, obviously, but cannot improve sufficiency of statistics. But I believe that in many situations we are forced to use Bootstrap. For example, in big data situations, sometimes we just have Bootstrap make by nature in our investigation. And that's why this theory can be quite actually useful.
Thank you very much for your comment. In time series, we don't have usually to have such a luxury as a sufficient statistic is next to impossible. It is next to impossible in time series analysis even to have a classical central limit theorem, as I was trying to show you in my talk. So many people doing time series believe, and I belong to this bootstrappers, let's say, church, that the only way really to process data and make reasonable decisions is via the bootstrap, because you don't have other means of actually doing, hierarchization of the data, identification of faults in vibration signals, or doing short-term predictions. So you are right claiming that Bootstrap will not be a panacea. Plus, you have to be extremely careful when you use Bootstrap, because not all there are many types of Bootstrap, and each type of Bootstrap is designed to a specific case. So I was showing you 3 cases of bootstrapping technique that are specific to my model.
We use also Bootstrap in case of the analysis of the data in case of the iris recognition. So it is not for time series, but also we try to get more info from small number of the data. For example,
that's another vector of another line of reasoning for Bootstrap. In time series, there is no problem of scarcity of data. In time series, there's a problem of, let's say, asymptotic distributions. But when you have scarcity of data and when you work with images, like I imagine when you do the iris recognition, then you can also use what is known as Bootstrap for, let's say, random fields. And I'm sure it will lead to very interesting results. But each time there are many people using Bootstrap that think naively that Bootstrap is a panacea. I'm very thankful to Professor for his comment regarding some deficiency of Bootstrap. And Bootstrap is not a panacea. And each time you work with different data structures, you have to think very well what kind of Bootstrap you are going to use. Because you have to think about this consistency.
Do you have any comments or questions?